computer. The floor is to George. Thank you. You are muted, George. George, you are muted.
Okay. Thank you, Kostas, for giving me the floor. It's a great pleasure and honor to start this year's Athena talks with a very good scientist and friend from India, Prasana Sahoo. So I will give a short introduction about him, and then Prasana will give you the floor to give us your very interesting presentation. So Prasana studied physics in the University of Calcutta in India, then studied in 2007 his master's again in physics from the University of Sambalpur, again in India, with a gold medal distinction, and then his PhD in physics again from Indira Gandhi Center for Atomic Research, again in India, with an outstanding thesis award. Then for his postdoctoral research, he moved to Brazil, Department of Applied Physics, Sao Paulo in Brazil. And then he moved to the University of South Florida in the US, in Tampa, to continue his work about transition metal dichalcogenides, where he did a very groundbreaking discovery for lateral heterostructures of transition metal dichalcogenides. I guess the topic he will present to us today. Then he moved to the University of Cambridge, Department of Engineering, when he continued his work about this very interesting topic of lateral heterostructures. And then since 2019, he's an assistant professor at IIT Kharagpur and also the group leader of the Quantum Materials and Device Research Laboratory. So, Prasana, it's a great pleasure and honor to have you here. Please share your screen and start your presentation. Thank you very much.
Yeah, thank you, Judge. Hope you can hear me. And Constantinos,
yes, you can.
And thank you for inviting to a great platform. And it's my honor to present the portfolio of your work here. Let me share the screen. Can you hear? Can you see this screen? Can you see the presentation?
Please place it in the full mode, Prasana.
Okay.
Share your screen again and place it to the full presentation.
Okay.
No.
Right.
Please switch.
Yeah.
Okay, now it's perfect.
Okay, perfect. Okay, thank you very much. And as George introduced, I will mostly talk about these emerging 2D heterostructures, but it is easier to stack them because the 2D material emerge because of it is easy to exfoliate them with a Scotch tape. That's pretty easier. You can make several kind of vertical heterostructure, but later on, couple of years back, it is also possible that because of their van der Waals nature, we can truly make them lateral heterostructure, direct growth. But this is not possible by mechanical exfoliation. One have to do only by direct growth. And with this talk, I will give an overview of this kind of lateral heterostructure, why this material will be very good for these things. Okay, so why we need to go to this kind of emerging topics such as new generation of material, ultra thin materials. We know that electronics is becoming flexible these days. We all are passionate to get more transparent devices, and we want high performance devices and very thin device. On this context, 2D material there is no alternative than 2D material. In terms of future smart mobile devices, for quantum technology as well, sensor and health monitoring, low power electronics display, and many more optoelectronic devices, including energy as well. Okay, so why today in terms of optoelectronics or electronic device, we know that conventional semiconductor cannot hold Moore's law because of their intrinsic limitation to their device dimension. Below a critical thickness limit, this conventional semiconductor such as silicon, germanium, these things, their mobility drastically goes down. So they will be no more useful for high performance transistor when one look for a thin transistor in principle, because thinner transistor is required, because you can imagine day to day we need lot of information to be storage, lot of processing, CMOS, lot of high compatible millions or trillions of transistor in a small chip. So that is not possible with conventional semiconductor, whereas in 2D material can give a complementary uh, uh, complementary to this conventional semiconductor in terms of mobility is very comparable, and this can be very easily we can grow them in a large scale, and also they are very flexible and transparent, so that all these terms like transparency, high performance, electronics, ultra thin body, all these things can be realized in one class of material. It is because it's possible because these materials they have weak van der Waals bonding between them, so that one can easily exfoliate the single layer. Single layer is still stable, and they don't have any dangling bond on their surface because of their scattering process at down to a single thin layer is minimum, so that the mobilities can be preserved, right? And the many other like leakage current, they can be grown large area with both for research purpose one can do mechanical exfoliation, of course for explorative research, as well as for industrial scale up one can grow them in a large area in at this moment. And the advantage is that this field is now boomed in such a way that people can get metal, semiconductor, insulator, all class of materials what one can realize in 3D dimension. One can get materials in 2 dimension as well. So the interest is when we combine this kind of different 2D material in form of heterostructure, either you integrate in vertical or lateral geometry, many more unconventional properties were emerged which were never realized in their bulk counterpart or even their monolayer counterpart. For example, graphene. If pure graphene is not superconducting, when we stack them in a particular twist angle, so it can show a superconductivity behavior. So like many more excitonic phases can emerge when you stack different kind of semiconducting phases. Before going to my topic, I will mostly focus on transition metal dichalcogenide because these are interesting class of semiconductor in these dimensions. So in these there are different kind of polymorph. We can get more semiconducting phase, metallic phase, and 3R phases. Because same material, but depending upon their crystal structure, their properties can be slightly varied. So that is also semi-metal is useful for you get for metal contact or contact engineering. This will be very good for that, or catalysis also. So this 2D semiconductor, you can say when I say single layer, this is effectively a sandwich between a tensor metal with the two chalcogenide layers, and this is roughly 6 Armstrong thick, so half a nanometer thick layer, and that give amazing optical and electronic properties. In addition, these materials have unique band structure because of their valence band is degenerated, that give rise to emergence of valuetronics or value hall effect, like many more new physics are emerging in this topic. One of the fascinating properties what I like is you can see that many materials, it is the optical properties depend on the amount of material, but here from bulk it is the indirect band gap material because of the peculiar band structure. When you thin down to a single layer, it is becoming a direct band gap semiconductor because of the quantum confinement effect and reduced dielectric screening. So that's interesting because you are thinning down and you are making the material more bright in terms of optics. Okay, so and there are many more new frontier in exciton physics. Exciton mostly the electron hole bound pair. Many conventional semiconductor, this exciton binding energy within limited to 50 to 100 millielectron volt. That's why they are mostly not stable at room temperature. whereas excitons in 2D semiconductors are roughly half a electron volt around. That means most of the photoluminescence that will emerge from this 2D material will be dominated by excitonic emissions. As well as in addition, exciton in this TMD can form different kind of complexes like trion, it can form biexcitons. All these have different quantum signatures. These are very good carriers for quantum information. In addition, depending on the type of substrate, one can choose like magnetic strontium titanate. One can tune the excitonic or this excitonic binding energy features. So one can modulate the excitonic features by suitably choosing different kind of substrate as well as engineering the structures. So more interesting recent as I discussed, because if you take a single piece of 2D semiconductor and stack another 2D semiconductor, what you see is formation of this Moore structure. This incommensurate structure sometimes is a source of quantum emitter that can trap particular exciton, and this can as arrays of quantum emitter from this. And that is interest is if we can same two set of material, but one can adjust the twist angle, one can modulate systematically these a range of emission and their quantum phases of the structures. So that way, many more unconventional quantum state one can access by adjusting this twist angle in addition to the choice of the two different combination of semiconductor. So in as a heterostructure, just to give you examples why heterostructures are the building block of many optical electronic devices, including high electromobility transistor, laser, solar cell, tunneling field effect transistor, that again depend on the type of band alignment. So why the 2D heterostructure? We see that in 3D heterostructure, suppose you take a P and N type junction, the depletion region is almost 100 nanometer. Most of the carrier can be either diffusion based or drift based diffusion. Drift is mostly when you apply voltage or diffusion. Okay, that means we need to, to turn on this transistor, we need to apply several voltages, volt to activate this kind of things. The more energy consumption will be there, to drift or the carrier to cross this depletion region. Whereas in 2D semiconductor, this device dimension already in the regime beyond the depletion region, we can see here. So no more extended depletion region can be observed in 2D geometry, where the carrier can be transfer is mostly can be governed by tunneling phenomena. Tunneling phenomena is a low energy is involved, and well as in terms of time scale, ultra fast time scale is involved. Ultra fast charge transfer can be occurred in terms of picosecond. Like many fast photo detector, this kind of application, this material can be ideal choice. So like this, there are many varieties of 2D material. One can play around, combine different kind of combination if somebody want to play around or want to explore many more different type of 2D heterostructure. And thanks to this 2D geometry, they can be vertically aligned like this. Two different semiconductor can be stacked. Their overall properties not in like a bilayer, but can be new kind of charge transport mechanism can emerge. For example, interlayer exciton, intralayer exciton. Those exciton lifetime is exceeded more than the exciton of the individual material. That's a long life exciton can be realized. That will be good, ideal for lasing or other emitter application. As well as one can do also lateral heterostructure. That's what it is very emerging, because it is not possible by mechanical exfoliation process. It have to be directly grown, because here there will be a van der Waals gap, but in this case they are perfect atomic interfaces, and they create a one-dimensional channel for carrier to move across interface. With that, why the interest in 2D lateral heterostructure? Because there are a lot of proposals in 2D form that this 2D lateral heterostructure can create a very stable and tunable 1D physics platform. For example, there are many unique properties such as Majorana fermion, plasma excitation, and spintronics application. Many things can be explored in this kind of 1D geometry. As well, one can realize, one can understand that in this 1D geometry, the interface exciton can be directional. One can appropriately design or engineer in such a way that one-dimensional transport of exciton can be realized in this kind of cases. And in addition, so there can be energy transfer in these cases. So there can be like electrical rectification, one can realize thermal rectification. Like many cases, to many, when we are trying to compact many transistors in small area, managing heat dissipation is a big challenges. So if this metal can also allow to dissipate heat in certain ways, like a transistor, there are rectifier which allow current in a certain way. Here also one can design such a way that directional heat transport can also be realized. So in terms of tunneling field effect transistor, lateral heterostructures. So this is the sub-threshold swing. This value decide how much minimum energy required for tunneling or switching a device. So lateral that is for conventional material, it is minimum is 60 millivolt per decade. So whereas for lateral heterostructure, it can go down below to 1 millivolt decade. But that way one can realize neuromorphic computing or tunneling field effect transistor which can operate in a very low voltage like our brain works, right? Very low voltage region. So with that, my plan is how we can create this kind of exotic structures. So what is there, how we can integrate them in a laboratory in situ ways, how we can modulate their phases in terms of electronic or charge, values or spins. So we'll show that in terms of integration, we can directly create multi-junction heterostructure using the chemical vapor deposition method. So where one can put all precursors and control the carrier gas and selectively deposit this 2D TMDs of different material. Like the novelty of our method is we use simple carrier gas switching rather than changing any other parameter. Simply we change we can, that's why we name it as a one part method. We put all precursor together, but by changing the carrier gas, we can selectively deposit one metal at a time. Then we study probe light matter interaction to understand what is the dynamic of exciton or light on these kind of heterostructures. Also exciton in terms of near field optics to see more locally within few nanometer area what is the optical behavior of the semiconductors. Also, a lot of majority of our work also recently we are doing more on fabrication as well as devices in terms solar cell, light emitting diode and photo detectors. Because the advantages of this method is these heterostructures, the tungsten related domain, they directly possesses like p-type characteristics. As molybdenum related domain, they possess n-type characteristics. You can imagine we are simplifying one step further that we can fabricate direct PN junctions in laboratory. Then PN junction, we know that they are the fundamental building block for many optoelectronic devices. Then in addition, recently we are also exploring many more engineering structure, to explore more new physics by combining spin, orbit, valley electronics, and along with their phases by selectively twisting them differently. Okay, so in terms of growth, there are several challenges because of that field, though emerged in 2014-15 around, but it was very challenging to grow them in a reproduced manner. So that's why the field could not expand. But in 2018, we could figure out a very novel and simple water-assisted method where we can able to create many more exotic structure like composed of molybdenum selenide, tungsten selenide, or molybdenum sulfide and tungsten selenide sulfides of multiple junction, superlattice, alloys, almost many way one we can control with our novel methods. That's a future great challenge is if you want to realize a practical device, one have to integrate different kind of dielectric, HB, and graphene. These are the grand challenge for this 2D community. Okay, so growth itself is a big challenge because silicon is today is very popular because silicon industry is very robust and we can grow high quality silicon. 2D material field is also same fate. Unless we can create very high quality semiconductor, this will not go to any industry, lead to any industrial application. Because CVD process, one can see here, very complicated because it involves several physiological physiochemical parameter such as temperature, flux, van der Waals interaction, edge energy, thermodynamics, kinetic factors, vapor phase precursors. We can figure out what are the important parameters that can affect in this prospective article. This temperature, pressure, precursor, pressure, carrier gas, substrates. So if you want to play around all these, then one, it will take enormous amount of effort. Although one can choose machine learning to also, of course, predict. However, we rather just fixing all other parameters variable quantity in order to selectively grow this kind of lateral heterostructure. That will go. All this we summarize in this book chapter. If you're interested, you can go through it. So in our CBD method, I'm not going more deeper into the fundamental aspect of CBD, but here in our one-pot CBD growth method, we named it as edge epitaxy. That means the epitaxial growth is not dependent on the substrate, it is rather on the crystalline edges of these preliminary islands. So here we use a carrier gas like H2O or hydrogen. Water is acting as oxidizing agent and hydrogen acting as a reducing agent. So all big bulk precursor will load into one high temperature zone of a furnace, and substrate one can place in the second zone at a relatively lower temperature. So how one can realize this kind of lateral heterostructure is, so when you allow into H2O, one can grow only molybdenum related molybdenum sulfide selenide domains. The moment you suddenly switch to argon and hydrogen into hydrogen, that will quickly stop the growth of molybdenum, now promote the growth of tungsten at the edges of the initial island. So this is how one can switch back and forth between these two parameters, then one can realize this kind of multiple junction without changing any other relative parameter. The process is very simple because this is a long story short. In order to validate this, we have to do several hundreds of experiments to validate this model. So what we figured out, when you put molybdenum bulk powder, when interact with the water, it creates local oxidation in it for molybdenum dioxide. That is becoming more volatile. It is gone, and molybdenum oxide related hydroxides that deposit on the substrate. Whereas tungsten are more, it is more stable in presence of water. So it form different multiple suboxides of tungsten, starting from tungsten dioxide to tungsten trioxide. Within that, there can be several suboxide phase it can evolve. But that was pretty stable in presence of water vapor that don't contribute to the growth. Whereas in presence of, when you change to reducing gas like hydrogen, so what happens? Molybdenum dioxide in presence of water, it quickly deplete into molybdenum, and molybdenum cannot evaporate at that lower temperature. But tungsten have a lot of preserved oxide, they start contributing to the growth along the edges of the initial molybdenum island. This is how one can change between stage 1 and 2, and that way one can use 1, 2, and 1, 2, like several multi-junction structure one can realize. You can see this is a single crystal because it is forming perfect triangular geometry. Okay, you can see multiple junction, one can go up to 300 micrometers crystal size, or even bigger depending on the requirement one can choose. So with this method, how we'll characterize these are individual domains. So Raman and photoluminescence, there is a fingerprint for 2D materials. So one can use, suppose you take a Raman map or PL map, then if you select this region of 1.62 region EV. So you see that only tungsten region is present. Whereas if you want to choose this region and map the whole area, one can see that only one molybdenum selenite, the peak corresponding to molybdenum, monolayer molybdenum selenite domains. These are, we realize that these are spatially distinct and they are connected. To not to confirm whether connectivity or whether physically distinct or not, one can take line map. That line map will give an idea about whether there is, how this material connectivity. And at that interface junction 2, so we can see that emergence of two distinct photoluminescence that indicating, and these not superposition state, because this kind of, when you take head of STM image, in head of STM image, STEM image, one can able to resolve sign atomic level images and lattice. One can see hexagonal phases of this, and the large area view I have put here because to see that for a long range what is the interfaces. Interfaces are relatively sharp because if you count number of particles, this will be roughness will be hardly into 1 to 2 nanometer. Whereas this was roughness is around, interface roughness will be around 5 to 6 nanometer. But in terms of optical properties, 5, 6 nanometer is very less. So in photoluminescence, one can get signature about sharp or diffuse interface. And there are also prediction that if you have a diffuse or sharp interface, one can modulate this recombination lifetime of exciton across the junctions. So if you have a sharp interface, it can prolong the recombinational lifetime. That means you can increase the lifetime of this carrier. This is for useful for certain applications, or it can be useful for depending on the modulation. One, if you want to modulate the emission characteristics. In same manner, this method is allowed to grow molybdenum sulfide to tungsten sulfide based lateral heterostructures. You can see that this geometry give different kind of truncated triangular geometry with this kind of structures. Even we can go further, we can able to grow concurrent bilayer lateral heterostructures, same way. Bilayer are interesting because they have direct exciton A, B, and indirect exciton. All kind of exciton can be realized in one material itself. You can see here we can get bilayer molybdenum selenite and superlattice, and WS2 one can get indirect exciton and A exciton. For MOS2 one can get B exciton, strong B exciton, strong A. At the interface we can get all PL signature. So it gives lot of more avenues for someone to study more different kind of exciton phases, interlayer, intralayer, indirect can coexist in this kind of structure. And this hard of STM image, one can see that one can get perfect atomic interfaces, so in this kind of bilayer heterostructures. So more later, like this method also allow the flexibility to mix or to form alloys of chalcogenides, maintaining this transition metal in individual domain, but chalcogenide ratio can be modulated or can be alloyed. One can still control the alloy compositions at individual domain, because this is essential, because for many solar cell or LED application, we need to tune the emission range or absorption bands. In that cases, our method is also possible that by suitably allowing with to mixture, one can systematically tune the individual domain within the heterostructures, the emission band from MOS2 to MOSC2 range. Similar for WS2 to WSC2 range. This it will give a complete flexibility in tuning the band gap at the interface. That is also essential, important for certain application. So what we can notice is from selenite to sulfide, this shape of the structure changes because some of the edge states, so depending on the stoichiometry, the edges can have different curvatures or different terminal. That also you can see here in these theoretical predictions, depending on the age states, they have possess a different chemical potential. Sometime they can also induce magnetism depending on the shape and the shape of the structure and termination of the edges. Okay, so as I told, we can form different kind of alloy. This is important because this band of offset is very essential for specific optoelectronic characteristics. Mostly the band offset between two type 2 heterostructure can be obtained by Kelvin probe force microscope. In that microscope, one use a tip and also sample surface to scan. And depending on the Fermi level alignment, there will be contact potential developed between the sample and tip. That contact potential give an idea about the band offset. If you calculate, you see here the FM topography of particular alloy ratio. So there is no height difference in the lateral geometry. That indicate all are in one plane. Whereas in Kelvin probe, you see this contact, there is a surface potential difference. From that, we could able to extract this contact potential difference of 132 millivolt. That is essential because if you want to extract certain device, there is a theoretical prediction again here. That is, you can see here, if you know to realize a bound exciton pair across the 1D junctions, one need minimum more than 150 or 100 electron volt of delta EV offset. So in our case, so that's what we can see here in all of the at different alloy compositions. So we can work function, we can calculate from that value that we can get more than 100 millielectron volt. That means theoretically we can expect a very strong charge transfer based exciton that can propagate along a line. That's more quantized conductance one can expect from a 1D junctions. And another aspect is this kind of lateral heterostructure can create in-plane dipole moment. In-plane dipole as compared to vertical heterostructure that can have different specific application. Okay, so now we will show you some optical characteristics because for optical these material are very emerging for optical applications and electronics. So we try to understand the optical properties of these materials because optical spectroscopy is very powerful tool for this 2D material to identify layer number, excitonic feature, sample quality, amount of doping, strain, valley physics, like many more. Valley physics for more important for quantum things. So using second harmonic generation, this is a second or nonlinear optical process that allowed material with inversion symmetry breaking. For monolayer TMD, for unit cell of TMD is a bilayer. In bilayer, their SS polarization are opposite, they cancel out. There will no SSG signal from bilayer. Whereas for monolayer, because of the inversion symmetry breaking, one can expect a strong second harmonic emission from a monolayer TMDs. That means you shine with a lower frequency excitation light, whereas you get your emission will be 2 times of your excitation frequency. That means you with lower power you can create high energy excited light, right? This is especially two photon absorption or is a resonance with the C exciton in this material. And SSG was often used people to identify layer number. One can see for 2 layer, 4 layer, there is no SSG signal. For even all odd layer, 1, 3, and 5 layer, one can even one single layer, one can get strong SSG signal compared to a 3 and 5 layer because of the diode band gap nature. Also, one can see that using that method, you can see here we by changing this tuning the light probe or excitation energy, we collect the emission range at a different frequency. You can see that in this region motor WS2 is excited more and At 440, the interface or enhancement are more. Selective interface enhancement occurs. At lowering from 425 to 555, then molybdenum domains are emitted in this range of frequency. And using polarized resolved SSG, second harmonic generation, what it is give a information about the degree of alignment between different domains. So this is showing the angular dependence of second harmonic generation imaging, and there is no mismatch between the emission petals, that indicating all the domains are coherently grown to each other. That means they are crystallographical, they are similar direction, and that is also indication that we expect there will be strain developed, but we don't observe any strain, and somehow the strain will relaxed during the growth. Okay, and there is strong enhancement across the interface, as we say, certain direction. That interface enhancement is because of the superposition of SSG signal emitted from different domains, that we confirmed by selectively blocking some signal from some regions to see that what is the origin of this second harmonic enhancement in these cases. Another low temperature PL is also another powerful tool to understand the nature of defect, trions, and exciton phases. So we can see that by different device geometry, appropriate choosing substrates or SBN capping, one can observe exciton, trions, bi-exciton in this kind of lateral heterostructures. But they exciton, bi-exciton, trions, they possess a unique power law behavior. So from exciton or trion, they show power of alpha value of 1. For higher exciton species, they can see higher power. Or if there is a defect, the alpha value will be less than 1. That from power law studies, one can study the nature of photoluminescence or presence of defect in this material. Because CBD grown samples are prone to some kind of defects because of intrinsic, because not high vacuum involved here. So in our case, we studied, these are recent results where we studied the photoluminescence spectra down to 3 Kelvin, where you can see that photoluminescence peak at room temperature is very broad because of the involvement of optical phonons. And also another to note it, these materials are directly grown from the CVD grown material. They are not exfoliated. And what are the sample? People see strong PL or narrow PL peak because they exfoliated and they were capped with the SBN, because they ruled out all dielectric, those things, confinement effect, or they reduce the dynamic screening. Whereas is a CBD grown sample, we have to, to understand what are the nature of a defect, whether it is coming contribution coming from substrates or it is intrinsic defect. We try to probe it. Down the line, we are up to 3 Kelvin, we see that exciton emission is quenching, whereas trion emission is enhanced at lower temperature, is intrinsic defect. So same thing we are observed in MOSC2, whereas in WSC2, we can see here there is a strong, the excitonic peak is still dominating up to 3 Kelvin. That indicating two factor, it may be it is a very high quality, though even if a mechanical explorer sample, it is hard to observe this kind of strong emission, even 3 Kelvin exciton emission, or it is a low carrier density. Okay, so to understand different kind of nature of defect, one can study here the excitons trion down to 4 Kelvin. You see the defect bands are prominent, and with the power law behavior, one can see here how the exciton trions are, and also defects peaks are emerging. So we can see here by fitting the power law behavior, so one can extract what is the origins of this kind of. So we can see here this green fitting where this alpha is close to 1 and all other are less than 1. So these are mostly defect are mediated. And again we did recent studies where we exfoliate this to a SBN layer. Then we saw that this defect band are diminished well. And this indicate that civil grown sample, because they grown directly on the silicon dioxide substrates. So there can be some kind of mild bonding between the CBD grown sample and the underneath substrates. That's why more defect are more prominent in CBD grown sample. It may be due to the substrate effect. Okay, same way we evaluate for the case of WSC2 monolayer to see, understand what are the nature of defect here. One in case of one thing we observed for WS2 and MOS2, the for at a room temperature, WSC2 for photoluminescent spectra is dominating over MOSC2, whereas at 4 Kelvin, MOS2 photoluminescent spectra is dominate over the WSC2. There is a transition from room temperature to 4 Kelvin, the photoluminescent spectra. This is because the peculiar band structure in MOS2 or SC2, the optically bright state is present below the dark state. That's what at lower temperature one can expect strong photoluminescence. Where for WS2, the optically active bright state is present above the dark states. So that at lower temperature there is a energy transfer, and that's why the one can expect lower photoluminescence from optically bright states as compared to molybdenum domain. This is why we can observe this kind of room temperature to 4K, this switching of strong photoluminescence behavior. Okay, now a couple of more okay, so next another 10-20 minutes I will cover the device aspects. So we say that 2D material have enormous potential for device applications. One can see that day to day number of internet of things or devices are increasing. One can expect 1 trillion interconnected device by 2035, which is amounting to $1.6 trillion by 2025. So sustainably powering such internet or small scale device is a challenging job, right? That's why there's the alternative that small, lightweight, portable, flexible, even self-powered in 2D devices are important. In this constraint, 2D material can be a great escape, route for us, right? We can see that 2D heterostructure, because by combining different 2D materials, one can use for different applications, starting from energy harvesting, flexible device, Internet of Things device, field effect transistor, photo detector, biosensor, memory device, printonics, excitonics, thermoelectric, photovoltaic light emission. One can almost achieve many kind of wide scale application of this 2D material. For today's talk, I will focus most on these for optoelectronic properties of the 2D heterostructures. As well as some extent, I will divide the electronic devices. Okay, field effect transistor characteristics. That is also interesting. So, as I told, in our case, there is a perfect. Unlike vertical heterostructure, since these lateral heterostructures are spatially separated, it is easier for device fabrication. One can spatially isolate it and create contact to this kind of device geometry. So it is easier than the vertical heterostructure to make device fabrication. Indeed, we did some devices like lateral heterostructure, as I told, MOSC2, WSC2. One can define source and drain by creating selective metal contact. For example, here we have a triangular geometry. You place the molybdenum domain in the inner triangle, outer triangle WSC2. You mask certain region with the boron nitride, and you selectively connect this region with the electron using electron beam lithography, this gold electrode. If you want to probe the nature of the MOC2, you have to do the study the electrical characteristics by using these two probe 1 and 5. If you want to study the interface, one have to do 1 and 2 or 4 or 5, so that we can understand the interface characteristics. First thing to do with electrical characteristics to check this contact, whether it is ohmic contact or not. We have realized this ohmic contact. Then by applying different back gate voltage, when you have a positive back gate voltage, what happen? Only MOSC to conduct electricity, because MOS to the channel will when you are applying a positive back gate voltage, you are populating more carrier in the channel. because you are applying more voltage, positive voltage, more carrier are attracted towards the channel. So it indicates MOSFET is a N-type material. For if you have a negative backgate voltage, what happens? All the positive charge carrier will drive towards the channel, so it indicates the channel is a P-type characteristics. So P and N junction. So what does that indicate? That the MOSFET domain are N-type and WSC domain are P-type. So we establish there is N and P. To establish this is a N and P, and if we are forming a junction, it should show a diode characteristics. Indeed, we did that. So now if you bias between 4, 5 and 4, either 1 and 2, what you can see that it behave like a diode. So and rectifier, that means it will allow only one directional flow of charge carriers. And diodes are perfect for to validate when you shine light of different power, the current increases. So that indicates your photocurrent increases, because when you are making PN junction diode, we have a depletion region. When the photon is impinging on the device, it can electron hole pair. The electron move to one side, hole move towards the WS2, and electron move towards the MOC2, so that electron hole pair is separated and one can get more and more current by increasing more and more power. And typical, and by analyzing, we get the photocurrent of up to or the order of 10 to the 5 to 10 to the 6, which is almost comparable with the standard transistors or diodes. So interestingly, with a bilayer, we got similar characteristics. In addition, one can get photovoltaic effect. So in photovoltaic effect, without any bias applied, zero voltage, zero applied bias. So by increasing more and more power, one can get more and more short circuit current. So that indicating this is a photovoltaic effect. Okay, because in solar cell, no one want to apply any voltage at zero gate voltage. By increasing power, you get, because of the inbuilt surface potential, inbuilt potential across the regions. When the light is falling, that because of the inbuilt potential, the carrier can effectively separate, and more current can one can harvest by increasing the power. So one can see here just 1 to 9 microwatt power, one can see tremendous increase of electrons constantly. Then details, short circuit current, VOC, open circuit voltage, photo, field factor, all these were extracted out of this. And of course, the power conversion efficiency one can evaluate, and this is very low. Obviously, one can imagine these are lateral geometry, very thin layer, and but if you want to realize the power density conversion, the amount of material used to convert this much power, this will be enormous. If you in terms of that. So we also realize, because since they are PN junctions, you apply voltage from the two sides, one can emerge this kind of strong photoluminescence, a light emission from this region. Okay, so this mostly light emission were more dominated in the WS2 side. There maybe we realize maybe up conversion happening, or there is some selective charge transfer might be happening in these cases. So for that, we are doing a lot of extensive work on devices, where we try to play around the contact engineering, so that we can make perfect N-type, perfect P-type, perfect N-type, and perfect TP type crystals, and with mobility up to 50, and here SS values, and also mobility for MOSI to around 80. These are high values compared to CBD grown samples. And also, if you compare the amount of current one can create with channel length, the values we obtain with this channel length is significantly higher than the any reported result. That means we are approaching towards creating electronic grade, because that is the next step towards applying this material for practical devices. Also, we are doing more like photocurrent mapping to understand what is the origin of the photocurrent emissions, what are the dominating regions. One can see here recent work that with just ordinary light, one can see a 3-time increase of photocurrent from this kind of device. So very recent, we are also trying to prove what is the origin of the device. We are playing around contact engineering because this take-home message is, to understand more deeper, there are a lot of challenges in this 2D material field. For example, one is contact engineering, because there will be Schottky defect, because that we probe here, we can see here in this kind of PN junctions. So one can expect high current emission from the interface, whereas we get more emission from the W, current appearing from W because of these contact asymmetries. So one can use all these factors, to get high efficient devices. Of course, for scalability, one can use machine learning strategy, where one can use, because one can imagine CBD have a lot of parameters, more than 12, 15 parameter can influence. So one can use all these variables, feed into machine, target variable one can set, and one can try to create electronic grade qualities. With that, I conclude my talk, and we can see that we can create this kind of a very exotic structure, is very cost effective and manner, and these are promising low power optoelectronics application. We saw that, and also some of the unpublished data we didn't show it. We got very interesting result on photosensor characteristics in these kind of devices. With that, I acknowledge my collaborator, previous groups, and recent collaborators on devices and optical studies, and thank you very much. And and you have feel free to ask any questions.
Thank you so much, Prasana, for this very interesting and detailed presentation about your previous and recent work on 2D materials, growth and application. So I would like to give now the floor to the audience for any questions or comments.
I have some questions, George, if you don't mind. And Prasana, thank you very much for your very nice presentation. I mean, indeed,
Thank you.
these 2D materials and these heterostructures, they provide new physics and new orders of freedom in order to build new devices. As I understood well from, and if this is the case, like your structures, they create and they formulate very low or very short depletion regions. This means that this is the reason why your devices or your structures are potentials for low power optoelectronics, I suspect, because you don't need any threshold. The threshold is very low in order to switch on your device. Am I right?
Yes, but however, this the contact is still is a big issue for 2D material. Because of the contact, still we need certain threshold voltage for this material. So at least few volt, if you see this kind of turn on voltage for our device, still it takes like few voltage. But again, these are backgate voltages. But I can come to the old data here. So still one need couple of voltage, drain source voltage, because contact is still playing certain role. Though the Schottky barrier is very low, one can play around these Schottky barriers, like choosing appropriate contact geometry, so that again one can reduce this threshold voltage. One can tune that threshold voltage, of course.
And what are the solutions? What the bibliographic research suggests in order to lower these barriers?
Yeah, one need, like there are several like semi-metal contact people are exploring. There are several nature paper recently people published. One is semi-metals to deposit. Another indium was a good solution contact. And very recent, because indium there is a challenges to deposit, because high temperature, slight light indium can melt. One have to apply, alloy it, so it is a very difficult task. So other formality, we are recently exploring different contacts like nickel, gold, platinum, palladium, all different contact to figure out which can give more best contact to this 2D material. We are working on that direction these days.
And I have a second question. Like, how can you fine tune this device? I can see from your presentation that by placing the heterostructures, laterally, like multi-layer structures, and by the rotation of the upper layer, somehow you can affect the physical and the electric,
Yeah.
the physical problem.
Mhm.
So I'm wondering, apart of the temperature tuning, because I checked through your presentation of that with the temperature tuning, you can tune the emission from the different, let's say, parts of your
Yes.
heterostructures. Can you rotate somehow, by fine tuning? I mean, can you make a short rotation of these layers by exploiting,
Yes.
for example, I don't know, probably piezoelectric
No.
effects?
Okay. So
How-
yeah. So that is part I did. That's our ongoing study. So I didn't present that. So indeed, we are trying to, like in some of our recent study, we're trying to make certain kind of heterostacking where you can able to rotate. I guess where it is. It can be. Give me some time because this device don't need to rotate. No, I think I missed it that. Okay. So this device what I am presenting here today, those are not stacked. They are directly grown like this. Okay, so for making heterostacking or different geometry, one need, one can mechanically exfoliate this kind of CVD grown sample, and we are also indeed working on that direction. One of my students, Suman, is working that, so we can able to control these twist angle between different flakes. So we saw interesting Raman characteristics, Raman features, photoluminescence characteristics in these cases, but we have not explored the device aspect of that. But what are the device result I was showing? It is nothing to do with the twist angle, because when we grow them directly, they don't have any twist angle. They grow in particular device geometry, and we directly use them, and we don't expect any twist during the growth.
Mhm, mhm. And
Is that clear? Yeah.
can I ask a couple of more that I have, if this is not a problem? Can I ask two more questions?
Yes, you can.
Because you share your screen and I cannot see the audience. What about Prasana electrically pumped? I suspect that this is not the case because you have the issue with the contacts. But what is the future of electrically pumped light emitting diode devices
Okay.
from
So
heterostructure material? What is the
yeah.
potential?
Yes.
Because we have some breakthroughs regarding organic similar devices.
Yeah, I understand. This material will not be comparable with the performance with 3D material, but you can imagine as long as you need a transparent material,
Yes,
atomical
correct.
thin samples, there is no alternative material that can match to these things. Okay.
Mhm,
Again, as I told, mentioned, the power density, like amount of metal used to harvest that much energy is enormous, because we
mhm,
are using just 0.6 nanometer thick sample, 1 micron, if you calculate the volume involved. So that is enormous. So, but photovoltaic community, we don't bother about single layer. Thicker layer works better. So like, so recently we are mostly focusing on bilayer or trilayer devices. We are not looking at monolayer. We observe bilayer giving more better stability as well as better performance. Now, I didn't see, we saw that in that last slide, we got current of several hundreds of microampere from bilayer device, which is really compared to the conventional 3D based devices. We are really working on that direction to really make electronic grade, materials. I think there is hope, and in terms of electronic circuit, there is a lot of application people are already showing, demonstrating, because large area TMDs can potential application if we can properly pack them or cap them with suitable dielectric material. One can use many different devices. People are already explored a lot of different devices using this 2D material.
Thank you. Thank you very much, Prasanna. Thank you very much.
Thank you.
Thank you, Kostas, for the questions and Prasana for the answers. Is there another question or comment from the audience? So I have one, maybe the last one, Prasana.
Yes,
I
sure,
saw
sure.
from your slides that you have, tested how sharp are these transitions from, for example, from tungsten to molybdenum? Is there any room for improvement, or how do you, I mean, how do you think it is possible to even further improve or tune
No, I
the
think,
sharpness of these junctions?
I got your point. So you see, this already we optimized. This is the initial result. So here you are talking about these things. So let me switch it. So these are old results. You can say this is 1 nanometer, but the recent one in the bilayer recently what we are observing. So these are very atomical sharp. They slightly hardly few atom. Because again you realize this is not grown on high vacuum. It's grown
But
on
Prasana,
absorption.
is this fully reproducible? Because if this is the case, you are ready for some interesting industrial.
Yes. It is very reproducible. You can see the Raman PL. In the PL map, we can see very distinct emissions. And also in the previous sample, you can see here, if there is a alloy, you can get a continuous band. But here, now we are frequently obtaining that part. We are frequently getting that. Before going for any device, we checked with the Raman map or the line map if it is it give distinct PL features. Then we realize this is a sharp interface.
Congratulations, very interesting. Nice.
Okay.
Okay.
Thank you.
Thanks a lot. I don't see any comment or question. Thanks a lot for your contribution, Prasana. Thanks for the audience for the participation.
Okay.
And we will continue next week. I don't remember who is the speaker, Kostas.
The speaker comes from robotics, area. I would like to thank, please, George, mute your. I would like to thank again Prasana for one more time. He was very generous to contribute to our community. We will keep informing about our activities, Prasana, and we are looking forward to meeting you in Crete. I think that
Thank you very much. It's my pleasure.
Arrange something and write some new proposals.
Thank you.
In collaboration with Indian universities in these 2D materials and the relative technologies.
Sure,
thank you.
Definitely.
Thank you very much, Prasana.
Okay.
Thank you, George.
I look forward to it. Okay. Thank you.
Bye-bye.
Thank you.
Have a nice weekend, all of you.
Thank you.
Bye.
Bye-bye.